Yeah, so I am Kevin Toerne. I work for ZIMEA. I'm a sales engineer for them. And I'll be talking about high bandwidth multi-camera systems with PCIe backbones. And we'll look at current and future technologies, applications. So we'll talk about cameras and embedded systems, and hopefully then I can show you how PCIe does it all. I had a bit more in here, but definitely my colleagues previously talked a lot about some of the other interfaces I was going to touch on a bit. But just a quick look at us. ZIMEA makes pretty much mostly USB and PCIe cameras for a large size range. So you can see here are our sub-miniature cameras going up to some of our USB cameras. And our PCIe cameras, you can see this is about the same size compared to these guys. These are about 1 inch on the side. For our much larger cameras, we do a lot of different things, but we try to make very small and very fast cameras with low power consumption, very rugged cameras, high bandwidth, high resolution, and we like to work with our customers to customize things moving forward. So some of the challenges to cameras in embedded systems. One of the first one is bandwidth, which is something we've been talking about, my colleagues previously, quite a bit. Especially in multi-camera systems, you can imagine you've got multiple cameras all trying to put their data into one data source, into one data processing unit. And that bandwidth you can run into a lot of trouble, especially if you need to have all that aggregated in one place. Either you need to save it, you need to process it to get some other information. And so high bandwidth can come along with either high resolution cameras, 4K, 8K scientific cameras running at relatively high frame rates, or even very small resolution cameras running at very high frame rates. And cabling, always a challenge. You often, even in these small embedded solutions, you still need to run all that data a long distance, either ribbon cables, fiber optics, and so on. So that's always a consideration. Obviously size, especially in embedded systems, again, smaller is just always better. The smaller you can make all your connectors, your cameras, and everything inside of it, the better. And of course, synchronization is always important. Very often, especially multi-camera systems, all those cameras need to be imaging all at the same time within very small durations. And they need to be looking at the exact same thing at the same time. So I just jump now just kind of straight into the PCIe camera interface. What are the pros and the cons of this? So ZIMEA in general, we've kind of jumped into this as one of our niche products, is the PCIe camera interface. And so why is that? So one of the first things and the primary things is the bandwidth. You're probably familiar with PCIe. With PCIe Gen 3, I believe we have 8 gigabit per second per lane. We have interfaces that use 8 lanes, so we get up to 64 gigabit per second in a single cable. You can do long cable lengths with PCIe. I show here a switch. We'll talk more about switches for PCIe, but you can see these are ribbon cable connections. But attached to this and underneath is a fiber optic connection, which can run 100 meters plus, especially at these very high bandwidths. We'll get more into that a little bit later. Another big advantage for PCIe is that latency. So first and foremost, the latency comes from just the plain and simply high speed. But second, when it comes to PCIe, there's almost no software stack. There's no other processor in between the camera and RAM in the CPU or GPU memory. So you can write more or less you're writing directly from the camera to a processor. And so the CPU in many cases doesn't need to be involved with that transfer. And so it can be freed up for other tasks, or you can write even straight to the GPU without involving the CPU as well. So you can start processing right away. And in most cases, the interface card between the camera and the CPU is really just a cable adapter, because now it's a PCIe interface. The camera just simply is an extension of the PCIe bus, and you write simply straight to RAM over what's essentially a cable adapter rather than some other type of controller or processor. And another advantage, of course, most all computers these days already have a PCIe backbone, so it's kind of already written into a lot of systems, and you don't have to transfer data in any way or rearrange your data so that it's compatible going into the memory. So some of the cons, of course, you know, pricing always comes into a play. Mainly where this comes in is when it comes to cabling, because there isn't really a standard for moving PCIe especially over long distances. Most of what's available these days comes from server farms, where they're moving large amounts of data in between servers at very high speeds. And so we take advantage of some of that. But we'll talk about the cabling a little bit later as well. But now I'll just kind of jump into the implementations of cameras in embedded systems, some of the applications, the computing platforms you might use for those. So just real quick, just a quick overview on a few applications. So there's medical applications, such as surgeons these days are wanting to overlay perhaps one particular band from a fluorophore that maybe that's lighting up where a particular tumor is or organ, and they can see that in real time. You can imagine these need to be very small, lightweight systems. Hyperspectral imaging for medical is becoming important. And of course, mapping, drones, self-driving cars, sports performance capture for movies, and manufacturing. We'll talk just a little bit more about all of these as we go. So mapping and survey, I kind of also write into here self-driving cars. You can imagine all of these systems very frequently have many cameras inside the same vehicle, looking at different bandwidths perhaps, or just looking at different scenes. All of that data sometimes needs to be at pretty high speeds, often going to a central processing unit, especially in the case of autonomous driving or drones. That data needs to be processed very quickly. The latency needs to be very low. So it becomes very important to have low latency and high speed moving to the central processing unit. And of course, mapping and survey, you have to move all that data, process it perhaps for color, or perhaps even to ortho rectify it, and then save it. And so you have to do that at pretty high speeds as well. Augmented reality, virtual reality, that sort of consumption of data from cameras these days is becoming more and more important and ubiquitous. You can imagine perhaps a realtor wants to sell a house virtually. So they'll walk through a house with a big camera looking all around and recording the entire scene, so someone can go back and look at the house virtually to see if they would like to buy it. Augmented reality, because now you can walk around and perhaps see something projected. You can imagine that data needs to be synced with the view of the viewer with very low latency. So all the input from the cameras needs to be very fast. And sports, sports performance is very important these days. You see here a motion analysis of a golf swing, very high speed, high frame rates. This is becoming quite common in a lot of places. You can imagine in stadiums, the speed with which they want to look at those players around the goals is very high, but as well, the cable lengths between each of those cameras can be kilometers at a time, all going to a central processing unit. They can now analyze in real time ball trajectories inside of certain matches. And again, cable lengths and processing speed, very important. Performance capture. This particular application, they're capturing the performance of an actor, actress in the middle here with many cameras. But then you can imagine after the fact, all this data can be collected and they can project that actor into almost any environment they like with given lighting and backgrounds. All that data is getting collected into, it's not always one processing unit in this case, but very often you can imagine the cable lengths involved here get to be pretty high, but the frame rates from each of these cameras are also high. So the computing platforms that you use to do all this, you can imagine first and foremost, they need to be small. They need to fit into very small spaces. The power consumption for each of those type of applications, because computing power and power consumption are antithetical, you have to be very careful of that in your design as you're putting all this together. And then saving the data at the data rates that we're often talking about here is often non-trivial in its execution. You really need to look at that closely, most often using solid-state hard drives and even RAID arrays. So just to look at a few examples of those that we've been involved with, the Nuke platform you're probably all familiar with. We tend to shy away from it a bit just because of its limited PCIe connectivity. You mainly have just an M.2 slot with only 1 or 2 lanes available. The COM Express is something we've gotten involved with personally. This is an example of a COM-E computer we've built up for our own use inside of production. These two so-called iPass connectors allow us to collect a total of 120 gigabit per second from multiple cameras, or perhaps just 2 of our high-speed cameras simultaneously, and process that data. So if we're looking for, well, we've sold this into a few different applications that can process the data looking for different things. And NVIDIA. NVIDIA, of course, is getting into this quite a bit. You're probably all familiar with them making video cards, but they've made a few of these very small embedded computing platforms like the Jetson and Xavier. The most interesting thing for us has been their PCIe incorporation. The Jetson has 4 lanes of PCIe available. The somewhat newly introduced Xavier has 16, so quite a bit of capability there. And NVIDIA is constantly innovating. There's already a new one on the way, I believe, with 32 lanes of PCIe. We'll see about that. But again, a very high GPU capability in these. That's the main point. The processing you can do with imagery inside of these is pretty amazing. Inside a very small package, just for scale, you can see this is the Ethernet connector. This is only a few inches on the side. So quite small and compact. And in comparison, power consumption is pretty low. The concept of a carrier board for these processing units is an important one. Up here is one of our custom carrier boards. There's also third parties making these for various NVIDIA products from Connectech that allow, in this particular case, direct connection to some of our cameras. Just to kind of jump into our own carrier board very quickly. Here, so this essentially, this small sliver here is the Jetson Nano, or excuse me, the NVIDIA Jetson. This is just the heat sink, and the rest of this is our carrier board. We've added a lot of things so you can develop with this, you know, Wi-Fi, connection for a monitor, and USB, but multiple connections up here for cameras for some of our PCIe and even USB cameras, as well as SSD for saving that data at high speeds. Another concept for PCI Express cameras and using those in multi-camera systems is the concept of the switch. Probably all certainly familiar with the concept of the switch when it comes to Ethernet cameras or Ethernet networking. This is basically the same thing. You can take the input from many cameras all at full speed, input them through the switch and out through a single interface at high speed running to the controlling computer. Just as a side note, so basically this carrier board is also a switch, and so you're able to input the data from many cameras through those lanes of PCIe directly into the Jetson. Here's an example of a few switches that we've developed and sell actively. For instance, this one can take the input from up to 12 cameras at full speed through this 64 gigabit interface direct to the PC. I've shown this picture quite a bit. This is a 360 camera switch we developed for a customer. Again, 8 cameras at full speed, outputting their data through a single fiber optic line to the controlling processing unit. And so PCIe can really do it all and help in a lot of different imaging circumstances. So PCIe helps minimize latency and really takes the CPU out of the equation, so it's freed up for other tasks. You're delivering data straight from the camera right into the processing RAM. You can support distances, obviously, from millimeters to hundreds of meters with fiber optics. We make a lot of different versions of our cameras, some with ribbon cable connectors or with direct so-called Firefly connectors. We've got more information on that on our website. We support, and obviously then you can aggregate multiple imagers onto one output through a switch. And because there's almost no software stack, looking at the data, processing it as it comes through, it's very fast, straight to RAM. And upcoming, obviously, PCIe, there's no sign that it's going anywhere. PCIe Gen 5 has just been starting to come out in computers. PCIe Gen 4 is quite common these days, which is, I believe, 16 gigabit per lane. And so it's just a really good camera interface for high speed and multi-camera systems. So in the future, Gen 4, as I mentioned, 16 gigabit per lane. It's becoming readily available in PCs these days. I believe the Xavier is a Gen 4 16 lane GPU basically. So the sensors that are able to take advantage of that aren't necessarily common, but they are always coming out faster and faster sensors. As my colleague said before, there seems to be no end to the need for faster and faster cameras and sensors. The cabling, as I mentioned, it's a bit of a Achilles heel for us at times. However, this is always changing, and we're taking advantage of newer connectors coming out from companies like Samtec with the so-called Firefly connectors. So just to wrap up, these are some links I've included in my talk. I believe you can download this talk later and go read up on more information. And with that, that concludes my talk.